Okay, so this is our week 7 assignment. So let us start with question number 1. So it's saying that the Hamiltonian, due to the interaction of a particle of mass m and charge q, the spin s of the particle with the magnetic field pointing along the z-axis is the Hamiltonian is given in a certain form, having this sz cap spin operator, spin angular momentum operator, and the Heisenberg equation of motion for the time dependent spin operator sxt can be written as what? So first of all, it is very simple that you have to use the Heisenberg equation of motion for an operator time dependence, and then calculate the and apply that equation for this operator a6t, which is the x component of the spin. And you know that inside that equation, Heisenberg equation of motion, this Hamiltonian term comes, and there you will substitute this Hamiltonian equation, and the successive commutator relation you have to solve, and finally you get to the solution. Okay, so that is the idea. So let us start solving it. So question 1 is that Heisenberg's equation of motion applied on A6 A6T spin operator. So the equation is basically that del A6 del T plus 1 by I h cap A6 commutator bracket. Now this part obviously will go to 0 because the spin operator, this has no explicit time dependence. I mean, it has implicit time dependence, but it will not depend on time explicitly, like some t to the power some power or some ln t. Nothing in explicit time dependence should come in a spin operator. That is why it goes to 0. And the only term you are left with is this commutator bracket relation with the Hamiltonian. Now in the question they have already provided us with a form of Hamiltonian, which is this, that h equal to minus qb by mc is z cap. Now in the final thing part, they have also, you can see they have also provided us with this relation that omega is equal to minus qb by mc. So you can follow this up that omega equal to minus qb by mc is something that is given towards the end of this question. So we'll be using that as well, and you get this is equal to omega is z cap. So Hamiltonian form is omega is z cap. Now you directly replace that here, so that now you can operate the commutator bracket with the spin operators is z cap and a6 cap, right? So, and omega is a constant, so it can come outside the commutator bracket relation. So it is basically a simple commutator bracket relation between sz cap and a6 cap. And you know that this answer is basically for any like this kind of an operator relation will give you I h cut s y cap obviously, but you have to see whether they are in a cyclic order or not, because that decides the sign. So s z and x will give you plus I h cut s y, because you go like this x y and to z, this is the cyclic order. So if you have uh, yeah, so in a cyclic order you go like this z and again back to x. So if you go like this, that you are at is z, and after that you have commutator bracket relation is x, so you will turn like you will come up at is y, but because it is following this cyclic order, so the plus sign will be there. But I cut is so this is basically a common commutator bracket relation you should already know. So we are directly using that. So and this I cut cancels out, and finally you get omega times sy cap. So this is your answer. But I think, okay, so we have to check whether, yeah, sorry, there has been a mistake, as I was seeing that sorry, my mistake. So obviously I have written down this term and the other way around. So this is Okay, so this is not this. So this is basically the Hamiltonian term comes in the second. So this is Sx cap comma the Hamiltonian operator. So because commutator relation, it is very important that you, that is why it is important that you memorize the formula well, because Hamiltonian terms, if I, if like last time I earlier I messed up with the order of the commutator bracket, so that is why I was getting a wrong sign in the answer. But actually the Hamiltonian term comes, operator comes in the second, and it basically becomes A6 cap omega S jet cap, and so omega comes out. So this is basically commutator relation of S6 and SZ, Sx and Xz. Now the whole sign reversal occurs because you are going from Sx, Sz, and you will turn up at Y, but now you are going in a wrong direction, which is not following the same sequence. You are going in an anti-clockwise manner. That is why instead of a plus sign, you will be having a minus sign, and the final answer will be minus omega Sy cap. So this is very important that you know the Heisenberg equation of motion in general, that dA dt for a general operator A is equal to del A del T plus 1 by I H cut A comma H. So the H term comes afterwards. So this is our answer, and this is basically our option number B, you can see. So option number B you are getting as an answer, minus, right? This is also the accepted answer. Now question number 2 is that the sum of two non-interacting angular momenta J1 vector and J2 vector is, so is given by, so this is basically an operator, so that is why this bold sign means they are actually operators. So J1, J2, and the total angular momentum is a sum of both of them, and they are non-interacting means there is no interaction or no intercorrelation between 1 and 2. Then which of the following commutator relation is correct? So here J square is the total angular momentum, which can be divided into components like Jx, Jy and Jz, and so we have to like say what is the correct relation. So first of all, these first two relations, if you look at, you will immediately see that they are wrong, because this Jx Jy commutator bracket relation, this is same as the Sx Sy commutator bracket that I just discussed to you earlier, because they are all like angular momentum relations. So no matter whether you take J or whether you take S or whether you take L, all are angular momentum operators. This is spin angular momentum, this is orbital angular momentum, and this is the total angular momentum operators. But for all these angular momentum operators, they follow a similar kind of a commutator relation, follow similar commutation relation. So like for J, I can write down that Ji J is equal to I H cut epsilon and epsilon ijk. This is the epsilon sign, epsilon which will decide the sign of that this commutator bracket relation. So this is jk. Now obviously, because if I and j are in cyclic order, then you will get jk, but this epsilon ijk value will be plus 1, but if they follow an anti-clockwise manner, then the value will be minus 1. So by this you will see that jx and jy will give you plus IH cut JZ, because X to Y to Z back to X is a clockwise manner rotation, and that is why the sign is positive. But if you have JY JX, then it will give you minus IH cut JZ. Similarly, so here you can, so these are known relations. I will not elaborate all of them, but the thing is that if you like in the same manner, if you have JY JZ, then you land up at plus IH cut JX. But if you turn if you like reverse the sequence of this JZ JY, and then you get minus IH cut JX. Similarly, the last one will be like JX JZ, because XZ will give you Y, but it is anti-clockwise manner rotation, so then it will be minus IH cut JY, and JZ JX will be plus IH cut Jy. So these are the relations. Obviously Jx, Jy will be following a cyclic clockwise rotation. That is why there will be a plus sign. So this is wrong. Jy, Jz again following a clockwise rotation. So there will be a plus sign with Jx. So this will also be wrong. So the only things we need to check our left options are C and D, and you have to check whether these two are correct or wrong. So or both of them correct or any one of them correct. So you have to formulate that. So let us derive this part here in the blank page. So we have in our hand that this is question number 2, that J total equal to J1 plus J2. Just one second. Okay, so J equal to J1 and J2, but they are both non-interacting. That means they are not interacting with each other in any way. So now we have to calculate what is J squared and J1 squared, right? So for this, what you have to do is, uh, so J is J1 plus J2 whole square. Okay. Now you can decompose this square part, the J1 square plus J2 square, and because this is these are all operators, so J1 J plus J2 whole square is not like a simple square operation, but it is basically meaning J1 plus J2 multiplied with J1 plus J2. So remember that they all have hat signs, even if I am not always mentioning it, but mathematically they are all operators. So J1 and J1, J1 squared, and then sequence matter. In case of operator, sequence matters, like because operators are like matrix, so matrix multiplication is not always commutative, so the sequence in which you are writing the operators always matters. So J1 J2 here it is, and the second term will be J2 J1, so both are different from each other, and then J2 squared. So that is what we also write here, that J1 J2 plus J2 J1 comma J1 squared. So this is basically J1 squared J1 squared plus, so you basically take out each term separately in under this commutator bracket, plus then J1 J2 J1 squared plus J2 J1 J1 squared. Now first of all, this part will be 0 because any commutator bracket relation with its own function will always give you 0, right? Because J1 and J1 are both functions of each other, same thing basically. But then J2 square J1 square will also give you 0 because J1 and J2 essentially they are completely non-interactive with each other. Since they are non-interactive, so that is why there is no commutator bracket relation. I mean, one second. So um, J1 square. Um, yeah, so there is no commutator bracket relation um, with this J1 and J2 also, because they are non-interactive with each other, so that will not, like, with respect to one, the other thing will be like constant. So if it is the case, then we know that for a commutative bracket relation with a variable and a constant will give you 0. So basically like that, in that sense, even if both are different operators, but because they have no interaction with each other, so as if with respect to one, the other one should is like constant, so you can take this part to 0. And similarly these are also like this can be at one look known to you that this is also is going to 0, because either it has its own function j1, which will anyway go to 0 with j1 square, and j2 is something that will also go to 0 for the commutator bracket relation with j1 square, because they are like non-interacting with each other, right? So this is like but even if you can decompose this part into terms, so this is basically giving you j1 squared j2 plus, this is the commutator bracket rule, how you decompose things like this, so j2 j1 squared. And similar thing you can also do up to this part and break it down into two terms. So the j1 with j1 square leads to 0, j2 and j1 square also lead to 0, because again non-interacting, and similarly these terms are also 0. So overall you'll see that all the terms are going to 0 and you are getting a 0 value. So obviously this commutator bracket is going to 0. That is one part. Now option number D also was giving you a similar argument that j2 square, j square and j2 square commutator bracket is how much. So if you just look at this thing that I have just derived, you can see that these are basically same, except for that instead of j1 square you have now j2 square, but basically it is equivalent, right? So you can already guess that this will also be equal to 0. If not, then you can also check for yourself that you put j2 square instead of j1 square and then derive the same thing like I did, and you will find out that the answer will be 0. So it's like we are getting the last two options are correct, because both are actually giving us a 0 value. So these are the correct options, C and D. Okay. Now number 3 question is that consider a wave function psi r theta phi, which is like c1 psi 1 n1 l1 nl m. This quantum numbers are given to identify the state, and similarly c2 times psi n2 l2 m2, which is a combination of normalized stationary state hydrogen like wave functions psi n lm. So these are like hydrogen atom like wave functions, which we are taking a linear combination of that with c1 and c2 as coefficients, and finally we are expressing this whole state psi. Now psi to be normalized, what is the condition that c1 and c2 needs to satisfy? Is it the mod of c1 square plus mod of c2 square equal to 1? So at a first glance we'll say that of course this is the condition that is true, because whenever you have a state presented as a linear combination of two other eigenstates, then given the condition that those eigenstates are already normalized and orthogonal to each other, the normalization condition on psi will be mod of c1 square plus mod of c2 square equal to 1. So that you can also mathematically derive it. How is basically that, let us check here that also mathematically we can show it, because it is a MCQ type question and these are like general ideas, so you do not have to like always mathematically and step by step calculate it for these things to be answered, but for the sake of doing it for the first time, I will show it how it is done. So how it is actually coming. So this is c1, then psi plus c2. Now we can also simplify the relation by writing it down as psi ket equal to c1 psi 1 ket plus c2 psi 2 ket. Now for this to be normalized, psi ket psi bra is equal to 1 if psi is to be normalized, and already the information is given that psi 1 and psi 2 are each normalized and they are orthogonal to each other. So that is giving you that this Chi kit. So in case of Chi bra, you have C1 star, then Chi1 bra plus C2 star Chi 2 bra with this commutator bracket relation sandwiched is the C1. Now Chi kit, you have C1 Chi 1 kit plus C2 Chi 2 kit. So this is the case equal to 1. So you multiply this with this, so that will give you C1 star. C1 is mod of C1 squared, then Chi1 bra Chi1 kit, which will obviously go to 1 because these are normalized. Chi1 and Chi2 each are normalized. Similarly, this will be, second term will be C1 star C2, then Chi1 Chi2. This will be going to 0 because they are orthogonal to each other. Then C2 star C1 Chi2 Chi1, which will also be going to 0 because orthogonal again. Then C2 whole mod square, which is C2 star C2, and then Chi2 Chi2. So this will also be going to 1 because they are normalized. So that is equal to 1. And finally you get the normalization condition on Chi as mod of C1 whole square plus mod of C2 whole square equal to 1 is the correct answer. So it's a condition for normalization of Chi, so you are getting that it's a true answer. Okay, so then it is also something that we have not only stated but also derived. So this is the answer. Now question 4 is that at time t equal to 0, the wave function of the hydrogen atom is Chi r comma 0 is this thing. Okay, so this is at t equal to 0, no explicit time, no time dependence is there. Then the subscripts are the value of the quantum numbers n, l and m. So the Chi has subscripts with 3 numbers representing n, l and m, 3 quantum numbers like respectively. The expectation value for the energy for this system will be how much? So you can guess that this kind of problem has a general notion. There are several problems that are given like this, but the general idea is that if Chi, the whole state, is written down as some combination of, let's say, sum over n, Cn, Chi n kit, where Chi n is the eigenvector, with a linear combination of which you are expressing the entire state of Chi, and let's say each of these eigenvector has a corresponding eigenvalue of En, which is the Hamiltonian operator. When it operates on Chi n will give you En, so energy eigenvalue. And each of the Chi n state being having Chi n in Chi is with a complex coefficient of Cn. So the probability of Chi state being in Chi n state will be like Cn whole mod squared, right? But in this case, when you there is a general concept that you can apply anywhere for a quick solution, that if you have to express the expectation value for the, like in this case the energy expectation value in this case, so what do you do is that simply the expectation value will be sum over n En Cn whole mod square. So basically you take each of these states, and the Cn whole mod square is basically this complex coefficient whole mod square is basically the probability of this state Chi being in the state Chi n kit. So this is the probability of the system being in Chi n, and the corresponding energy eigenvalue is En. And such thing can happen all over the values of n, so you have to take a summation of n. So that is a general idea, that is a quick thing to check questions like this. You can also check for yourself that this obviously becomes the case when you have an expression like this. Like you can take expectation value of the Hamiltonian, which is basically your energy expectation value, which acts like you have to operate Hamiltonian sandwich between two Chi kate and bra, and then you can express each of them as Cn star Chi n bra, and then H cap, and then sum over n Cn Chi n kit. And because these Cn star Cn are simply, they are, I mean, constant terms, so they can come outside the integral. So there is a common summation taken over all of them. Cn star Cn comes outside the integral. You have Chi n H cap Chi n. And you know that each of these eigenvector Chi n and H is sandwiched in between. That is actually your energy eigenvalue or energy expectation value. for this state n. So that is en basically, and this is cn whole mod square sum over n. So that is how you get this solution. Okay, and now we can directly use it, that in here you have where you have this um, expectation value of the energy, right? So like psi 100 you have on the first case, which is for n equal to 1 because n l m m, and then psi 210 has n equal to 2, then psi 211 has n equal to 2, and then psi 21 minus 1 also has n equal to 2. So an LMM, you do not need the information for that because energy eigenvalue has only this depending on this index n or quantum number n. So the solution will be uh, solution. So let me give the solution here on the side of it instead of going down in the page. So the solution will be energy, total energy expectation value is sum over n cn whole mod square en. So for the first case where psi 100 is used, that is n equal to 1. So at the outside we have a constant common factor of 1 by 10, that is 1 by root over 10 whole square basically, because you are anyway taking the coefficient whole mod square. So the 1 by root over 10 will get squared and 1 by 10, and then 2 squared times e, so this is basically becomes 2 squared times e1 plus 1 squared, because there is no coefficient here, so it is 1 squared uh, e2 whole squared plus sorry, not squared, e2 plus then root over 2 whole squared times e2 again because n equal to 2 plus root over 3 whole square e2. So what you get is that 2 squared e1 plus 1 squared e2 plus root over 2 squared e2 plus root over 3 squared e2. So which is like 4 e1 plus 1 plus 2 plus 3 e2. And also we should not forget the 10 outside, which is 1 by root over 10 whole squared. So this is basically the constant coefficient, so it is 1 by 10, which is like 4 e1 plus 6 e2 by 10. So this is our energy expectation value answer, 4 e1 plus 6 e2 by 10. So the correct answer will be option number D. Okay, now question number 5. So this was our solution for question number 4, of course. Now question number 5 is the gates J and M are simultaneous eigengates of total angular momentum operator J square and its Z component Jz with eigenvalue J, J plus 1 each cut square and M each cut respectively. Then J plus Jm and J minus Jm are also eigengates of J squared with same eigenvalue. So you have to say whether that is true or false. So from the lessons, if you have followed the lectures, you will like, you don't have to even solve it, you already know that it is true, but you can also mathematically show it, and that I will show that whether, if you don't remember the answer, sometimes you can mathematically check it out, right? So basically it is saying that first of all, this J square is an operator when it operates on an eigenstate Jm, which is basically it's a total angular momentum operator. So it gives this eigenvalue J into J plus 1 each cut squared Jm. But there is this Z component of this J operator, which is Jz, which has also this eigenvector as Jm, which will give you m times h cut Jm. So these are the two eigenvalue relations. Now there is the mention about what was the thing? J plus minus, right? So J plus minus. Now J plus minus expression is that it is uh, Jx plus minus I Jy. This is the form. Now you can take a commutator bracket relation J square and J uh, plus minus, which is basically like J squared Jx plus minus I Jy. Then you can again decompose that this is j squared jx plus minus I. Now you know that each of the term will go to 0, because that is what you must have learned in the lecture, that any component of j, whether it is x, y or z, with j square will always give you a 0. So how that is true? That because let's say j square and jx, how that is 0? So let me check that. So j squared means jx squared plus jy squared plus jz squared and then jx. So this is jx squared jx. So this will obviously be going to 0 because it's the same function. Jy squared jy plus jz squared jx. Now each of them will be giving you uh, so jx squared jy squared jx is basically this. So here we get jy jx is basically jy jx is again minus I cut jz. And x will give you z and x, so it will give you plus I cut jz jy, and this is z and x will give you plus again I cut jy. So that is how you end up at j square jx equal to 0, and by similar thing, if you can derive it by yourself, that you can also check j square jy is also equal to 0. So here this j square has this combination with jx and jy. So okay, so you are in the middle of the solution for this question, where we needed to this question number 5. We needed to find out, we have this information that j square and jj z are two operators that has this jm as their eigenstate, and these are their respective eigenvalues. Now we had to prove the statement whether you can say that j plus minus this operator when acting on this jm state, will that be also an eigenstate for this j squared operator and jz operator with the same eigenvalue? So that is something that you needed to prove, right? So then so let us go back to the question once again. So question number 5 was that uh, you had to prove j plus on j m and j minus acting on j m are both eigenkets of j square with the same eigenvalue. So for that, what we did is that we first of all expressed what is j plus minus operator form, that is basically jx plus minus I jy, and then we have to first find out the commutation relation of j square and j plus minus. So that we wanted to find out. So for that we can divide it into parts and separate it into j square jx commutator relation plus minus I times j square jy commutator relation. Now it is a well known thing, if you have solved this, studied this part of angular momentum operators in quantum mechanics, that this j square with any component of j will always give you commutator bracket 0. That you can also derive for one of them, like you can take j as jx component and then solve it, and you can decompose the j square as jx square plus jy square and jz square summation, and then when you take separately each of the terms, you will get that you have this kind of a form, right? Jy jx and this kind of a form is there. So that basically gives you that this jx square jx becomes automatically 0, but this jy is jy jx plus jy jx jy, right? And then similarly for jz, then you can say that jy jx equal to minus I h cut jz, so that is there, and jy jx is again minus I h cut jz and then jy. So there is a sequential difference at first jy then jz, and in the second term jz is first and then jy. Similarly for jz jx, you can write down that this is I h cut jz jy, and then similarly for this one. So this whole thing becomes 0, and similar thing you can also prove for that jx square jy is also 0. That I am not solving, for that you can check for yourself if you have, if you want to at all cross check. So that is the thing. So if both of them are individually 0, then obviously the whole thing becomes 0. So now comes the main factor, that if this commutator relation is 0, that means j squared j plus minus minus j plus minus j squared equal to 0, which is the like relation of commutation when you decompose it. So that means also that j squared j plus minus is equal to j plus minus and then j squared. So they commute with each other. That means you no matter at what sequence you take them, whether you take j squared first or you take j plus minus operator first, but it actually gives you the same result. Now that is a prime factor, that if you have this relation, then now let's say you take this form that j square j plus minus this operator is acting on this state j comma m. Now you already from previous from here you know that j square j plus minus can also be written in a reverted sequence, that is j plus minus first and then j square. Now this acting on jm. Now what advantage does it give you is that in the first case you had j plus minus acting on this jm, but you directly do not know the eigenvalue relation of j plus minus with jm. Like you also do not know whether this jm state is an eigenstate of j plus minus or not. So what you instead do is that you invert, like you change the sequence of these operators, and now you have j squared acting on jm, which is a known relation because it is an eigenstate of j squared already, that is given you to the in the question. So that eigenvalue equation, you can write that this is the eigenvalue j into j plus 1 each cut square and then jm, right? Now once this is done, you know that j into j plus 1 each cut square is just a constant, so it's not a state or something, so it comes outside, and this operator j plus minus will solely act on this jm state. So what you get from here, that go from here to here, is that j squared, let's say this is acting on this new state which is basically formed by j plus minus operator acting on this jm state. So this can be renamed as an entirely new state. Let's say this is a new state, and this is equal to its eigenvalue becomes j into j plus 1 each cut square, which is a constant term, and then similar thing you also have here, that j plus minus cap j m. So this is a state and this is a state. So basically you have this operator j cap square, which is actually showing that j m is an eigenstate of j square with this eigenvalue j plus 1 each cut square, and similarly due to the commutator relation being true, you also can say that j plus minus jm is also an eigenstate of j squared with the same eigenvalue of j into j plus 1 each cut square. So this is the eigenvalue, same eigenvalue. This is the entire new eigenstate. So Jm is an eigenstate, and also J plus minus acting on Jm is another eigenstate with the same eigenvalue. So this statement is true. So out of these two options in question number 5, we will say that this is true, that we have just solved. Now question number 6 is, one real operator A satisfies the equation a square minus 5a plus 6 equal to 0, then is A an observable? So first of all, this is a very basic condition in quantum mechanics, that for an operator to be an observable, it must be a Hermitian operator. Why? Because Hermitian operators have this property that their eigenvalues will always be real, and the eigenvectors will correspond to, for eigenvectors corresponding to different eigenvalues, will be orthogonal to each other. So that is the basic condition for Hermitian operators. And because these are satisfied, so it is a known fact of quantum mechanics that for a operator to be real physical observable, it must be a Hermitian operator. So Hermitian operator condition you already know probably from earlier classes, that Hermitian operator means it is self-adjoint, that is A cap operator is just equal to its dagger operator A dagger. So now this using this a squared minus 5a plus 6, let us see whether this operator matrix will give us real eigenvalues and what are its eigenvectors, and whether once we do that, we can also solve for what is the form of this operator A in matrix form, and then from there we can see whether A equal to A dagger Hermitian condition is being satisfied or not. So the equation given in terms of A is that A squared minus 5 A cap plus 6 equal to 0. Now once you have this kind of a relation, you know that although this is a equation like that, but it is basically a matrix form equation, because this 6 means this is 6 times I, right? But then to solve it simply, you can say that, let's say lambda is the eigenvalue for this operator A cap. That means A cap can be written in a diagonalized matrix form, where the diagonal components are the eigenvalues lambda 1 and lambda 2. So the from a matrix equation, this condition tells you that if you know the eigenvalue, then you can simplify this in eigenvalue form, that instead of writing down the matrix, you can write down the eigenvalue lambda square minus 5 lambda plus 6 equal to 0. So lambda square minus 3 lambda minus 2 lambda plus 6 equal to 0. And then when you take lambda in common, so lambda into lambda minus 3 minus 2 lambda minus 3 equal to 0. So then you get lambda minus 3 lambda minus 2 equals to 0, and you get the eigenvalues as 2 and 3. So once that is done, so then so you know the eigenvalue. So now you can say what is the rough form for this operator A cap, because you know that if you know the eigenvalues of a matrix, then you can always represent the matrix in a diagonalized format, and the simple rule is that the eigenvalues will be the diagonal components and the off diagonal components will be 0. Since it is a quadratic equation, so that is why you get two eigenvalues, right? So this is a quadratic equation, you get two roots from solving a quadratic equation. That means you have two eigenvalues of the matrix, which also tells you that the matrix is a 2 cross 2 matrix, because then the diagonal components will be the two eigenvalues. This is the diagonalized representation of the 2 cross 2 A matrix, where the diagonal components are 2 and 3. Right, so this is clear. And then you can already see that the eigenvalues are real, so which is a basic property for the Hermitian operator. That is not a sufficient condition, although the primary check will be to say whether A equal to A dagger or not, but you see that eigenvalues are real, which is also important criteria for an operator to be observable, because it measures a physical quantity, right? So it has to be real eigenvalues. And so we can check whether this is Hermitian or not. So A dagger, let us we do A dagger. A dagger means you take transpose conjugate. So you take transpose of A and then conjugate. But here the conjugate thing will not do anything else because all our eigenvalues are real. So there is no complex conjugation doing anything extra. Only the transpose will get you row to column and column to row. So but you see that if you take column to row, it becomes 2 0, and if you take this column to row, it again is 2 0 3. So it's basically the same as the main matrix. That means A dagger equal to A, that means it is self-adjoint or it is Hermitian. That is proved. And also it has real eigenvalues. It is Hermitian, and also you can get down to the eigenvectors that it has correspond to those eigenvalues and check whether those are orthogonal to each other or not, because two different eigenvalues will give you two eigenvectors which will be orthogonal to each other if the operator is Hermitian or it represents an observable physically. So then how to do that is that you take the matrix 2 0, you take the eigenvector as, because it is a 2 cross 2 matrix, so the eigenvector will be like two terms like this. This is a eigenvector form, and then lambda 1 is, uh, let's say lambda we see first, and then you have also x1 x2. So what relation it satisfies is that 2x1 plus 0 times x2 is lambda x1, and 0 plus 3 times x2 is lambda x2. So when lambda equal to 2 for a one eigenvalue, you see that 2x1 equal to 2x1 is satisfied, but 3x2 is not equal to 2x2 in that case. That means here this condition will not be satisfied unless you have x2 equal to 0 should be taken for this to be justified. Only then 0 equal to 0, this will be justified. So that means you have, for lambda equal to 2, you have x1 x2 is equal to, simply x1 you can simply take as 1, so x2 is 0, so it's 1 0, and it's already normalized in this case, you can see, because the eigenvectors need to be normalized also. And for lambda equal to 3, you have 2x1 equal to 3x1, which is obviously not true. So this will only be true for, again x1 equal to 0 has to be taken, but on the other hand in this case 3x2 equal to 3x2 is satisfied, so you can take x2 equal to 1 and for the simplest choice, and then for lambda equal to 3 the eigenvector becomes 0 comma 1, which is also normalized, you can see. So you have your operator A, which is you can see that it is Hermitian. That means A dagger equal to A. It has two real eigenvalues 2 and 3, and the eigenvectors corresponding to those two eigenvalues. So eigenvectors are each normalized and orthogonal to each other. Why orthogonal? Because you can see their composite product becomes 0, so inner product basically. So how do you check that also? That if you take let's say one eigenvector is psi 1 and the other eigenvector is psi 2, so orthogonal means this becomes 0. In other terms, psi bra can be written down as 1 0 in bra form will be 1 0 in along row, and 0 1 along column, because it is a kate, so that is equal to 1 times 0 is 0, 0 times 1 is 0, so this is 0. So this is orthogonal. As you can see that this is orthogonal to each other. So all these conditions being satisfied, we can say that A represents a physically measurable observable, physical observable. So this is question number 6 then we have done. So question number 6 is this, that okay, A is yes, this is an observable. Now question number 7 is, using the concept of parity, find out which of the following integrals are non-zero. Okay, so there are several integral relations given with s, p, y, these orbitals. These are the functions in integrals as hydrogen-like wave functions. So these are hydrogen-like wave functions giving you these orbital 2s or 2px, 2py, etc. These are hydrogen-like orbital wave functions. Now, you know that when an integral will be 0 and when an integral will be non-zero. So, if these are like inner kind of like expectation values, so the integral limit you get that this goes from minus infinity to plus infinity, right, in terms of x or dx something. So, here this kind of an integral becomes 0 when the integrand function that is inside the integral, that is an odd function. When the integrand is odd and this is non-zero, rather it will be like 2 times 0 to infinity this dx. This happens non-zero result when the integrand is even. So even and odd, by that what do you mean is that when you change the sign, let's say if you have x, then you change the sign, it becomes minus x, so that is basically odd. But if you have, let's say, x squared and you now put x to minus x and then again take a square, so it remains x squared, right? So then we say that this is an even function. So this even and odd is in terms of the parity. Parity means you change the sign to the like position coordinate, like in this case x for one dimension, and whether that function remains same with from because of x to minus x, then if remains same, then we'll say that it is an even parity, and if it does not remain same but there is an additional minus sign, then we say that this is an odd parity. So parity means you are changing from position coordinate from r to minus r and seeing change in the other measured quantities for that, seeing changes because of this in other physical quantities. Okay, so now carefully look at this solution equation, that you have the orbitals 2x, 2s, 2py, 2px and 3d, and inside you have x, x squared and x. So first of all, let me write down this question number 7 is, under parity operation, what actually happens to this different component. So first of all, x is odd parity because you know x becomes minus x, okay, but x squared is even parity because you know that because of x to minus x, x squared remains x squared, but from x to minus x, x becomes minus x, so that is why it's an even parity, odd parity. Now we have information about these, but we do not have information about these orbitals that are given there, like 2s, 2px and 2py, and I think 3d was there. So all these, so these are like hydrogen atom like orbitals. So from there you know one thing, that how is the parity represented in terms of these orbital wave functions or orbital states, is that this is minus 1 to the power L is the parity formula, where L is the quantum number that represents one of these orbitals separately, like L equal to 0 is for s orbital and L equal to 1 is for p orbital, and so for p, all px, py and pz are all with L equal to 0, and L equal to 2 is for d orbital, so all everything in d will be for L equal to 2, and L equal to 3 will be for f orbital. So these kind of thing will happen. So that means for this state 2s, which is basically s orbital, that means L equal to 0, you have the parity as minus 1 to the power L equal to minus 1 to the power 0 equal to something to the power 0 equal to plus 1. So this is basically this parity of 2s state is even parity. Now for L equal to 1 to px, this is equal to minus 1 to the power 1, this is minus 1, so this is an odd parity. Similar thing will happen also for 2py, so this is also odd parity, and 2pz is also odd parity. So you are also left with 3d. So d means L equal to 2, so that is minus 1 squared equal to plus 1. So this is again an even parity. So just like that, you have separately now known all the different terms parity behavior. But then when you combine all of them, you have this integral equation will come to the picture, which will give you this something like inner product and something like expectation value in x. So what happens is that if in the integrand is even overall, then it will be a overall even thing, and the integral result will be non-zero. But if the integrand is such that the all three terms separately contributing will give you an odd overall integrand, and then it becomes zero under symmetry interval. So that is what we need to check here. Like in the option number A, you have x as your odd parity, then you have 2s also as your 2s as your even parity, and 2px is as your odd parity. So you see that odd and odd will cancel out each other and become even, and this with even will already be even. So the whole thing becomes even in parity, and so the this product value will be, this expectation value sort of a product value will not be equal to 0. So A is non-zero. Then second question is taking x squared and then 2x 2px. So 2s x squared 2px. So this is for even parity, 2px is for odd parity, and 2x is for even parity. So even and even will be counted as even, and even and odd will make it odd. So it's overall and odd parity. Then this one where x squared is even, 2px and 2px on two sides, they are actually odd. So odd and odd two times makes it even. So this is even. So this whole integrand is not equal to 0. Okay, and then um, so I think need to, like, let us take a page and then show it which one of them are 0 and which one are non-zero. So this is question 7 continued like that. And so you have these terms like, which option number A was 2s x 2p y. So out of which 2s is, we saw that this is even, x is odd, I told earlier, and 2py is also odd. So even, odd and odd will make it even in general, in overall. So the integrand when taken from minus to plus infinity is not equal to 0. And the second case was that 2s, so here this is even, here this is even, but here this is odd. So even and even, but even and odd makes it odd. So this is overall odd. So the integrand will be equal to 0. Question number 3 is, this is even, this is also uh, sorry, this is even, but this is odd. This is even, this is odd, and this is also odd. So two odd and odd will make it even, and even is anyway even. So this is also even, and the integral will hence not be equal to 0. And question number, option number D was 2 px x 3d. So here x is odd, 3d we saw d orbital will be even and p will be odd. So two odds will make it even, and even will again be even. Since even, so the integral is not equal to 0 in the three cases. Only the option number um, not equal to 0 in three cases, right? So the option number A, C and D all will give value not equal to 0 from the integral relation. So we had to find out which of the following integrals are non-zero. So whichever ones are giving us non-zero value are A, C and D. So that is the correct answer, that A, C and D are giving you non-zero integral results. So that is true. And question number 8 is, consider a system in the state psi theta phi equal to this y1 minus 1, y0 plus y11. So here this is a representation where this y subscript, these two numbers are basically y, l comma m. So the measuring probabilities of measuring LZ with m equal to 1 will be how much? So this out of this a y l m, so now we have to find out where is m equal to 1. So for m equal to 1, you only have here y 1 comma 1. So the system for the state to be in this eigenstate y11 is has some probability, which is basically its coefficient root over 3 by 5 and whole mod square, right? So then for m equal to 1, the probability will be so then probability of measuring, as I said, that probability of measuring LZ with m equal to 1 is same as the probability with m equal to 1 is the same as the probability of the system to be in the probability of system to be in the state y11 theta phi. So what is the probability of y11 theta phi out of this psi is basically y11 . So this option will be this whole thing whole mod square. That means if you have this whole mod square, then the probability will be this whole mod square is equal to 3 by 5, which is 0.6. So this answer will be 0.6. Okay, so this is also done. Then question number 9 is that consider a system of two non-interacting identical particles of mass m confined into a 2D box of sides a. Then the energy of the system in the state psi 2, 2 x1 y1 and psi 1, 4 x2 y2 will be m square pi square h cut square by 2m a square. Then where n is at what value? So first of all, you were talking about 2D particle in a box case. Okay, so particle in a box problem eigenvalue you already know, and then for 2D there will be an extra additional component coming in the plus sign of energy from the different dimension altogether. So that is there, and two non-interacting identical particles are there. So two identical particles are there and they are non-interacting with each other. So in such case, the energy of the system is given by will be in the state psi 2, 1, 2, 2, 2 x1 y1 and 1, 4 x2 y2. Then where n should be what? So question number 9. The particle in a box problem is that in each dimension you have n square pi square h cut square divided by 2m square. So the box has a side of a, and then you have two 2D particle in a box. So you have also this n2, which is capital N square pi square h cut square by 2m a square, where capital N square equal to small n1 square plus small n2 square. So this is the relation. Now you have actually two particles, two non-interacting particles. Two non-interacting particles means there is no interaction with themselves, so that therefore their total energy will be just the summation of the two energies. Total energy will be total energy sum of particles individual energy levels for this particular state. Like in this case, the energy required will be um, that means for identical particle 1, which is at 2, 2 coordinate, where this 2, 2 will give you 2 square plus 2 square equal to n square equal to 4. And for 2, 2 is basically becomes now 1, 4 square, and this is again 1 square plus 4 square equal to 6. So the total energy for the whole system The total energy will be um, in square value is square plus 2 square is 4 plus 4, actually this is 8, and 1 square plus 1 square is 4 square is 6 plus 4 square is 16 plus 1 is 17. So total n square is 8 plus 17, 25. So here this whole expression n square will be replaced by 25 and hence n will be 5. So the answer is 5. Now last question is in the simple harmonic oscillator problem, the creation and the annihilation operator forms are given like this in terms of x and p operator. Then the value of the commutator a dagger is how much? So if you know if you have studied and solved the harmonic oscillator problem, this MCQ can be easily and directly answerable, that this a dagger will always give you the value of 1. Okay, so if like that, then we can start also deriving it and show it that whether it is actually coming as 1 or not. So let's say so a form is root over of m omega by 2 h cut x plus I 1 by root over of 2m. And then a dagger so what are the forms? Let me see again. So a equal to some root over m omega by 2 h cut x plus I by same thing p, and then this minus I for a dagger is for x and p. Then a dagger minus a dagger a will be okay. So a dagger is then becoming root over m omega by 2 h cut minus this. If you take consider all of the commutator brackets separately with care, then you see that first term is x cap is already going to 0. minus the term is root over m omega, and bottom m omega cancels out, so this is I divided by 2 h cut I squared is minus 1 minus I squared is plus 1, so 1 by minus m omega by 2 h cut x cap minus I by 2 h cut this this is xp, and then this is p comma p, right? So this is 2 h cut px so this is minus m omega by 2 h cut x comma x minus I by 2 h cut x comma p minus minus plus I by 2 h cut minus and minus plus, and again a minus I square is minus 1 2m h cut omega. This is 0, this is 0. Okay, so you are getting minus I by 2 h cut into I h cut plus I by 2 h cut into minus I h cut uh, minus I by 2 h cut into I h cut. So this is equals to, it becomes I squared is minus 1, so again minus I squared h cut by 2 h cut is equal to minus I squared by 2 minus I squared by 2 minus I squared by 2 this is just 2 as below, and then 1 by I h cut minus I squared. Okay, so first of all, I think we are anyway stretching it less than it's required, so greater than it's required. So let us redo it. So we had to check whether a dagger is equal to some relation. So we put the expression of a directly, which is root over m omega by 2 h cut x plus expression of sorry, this is the whole expression of a includes root over 1 by root over 2m h cut omega p comma root over m omega by 2 h cut x cap minus I root over of 2m h cut omega p cap. So this is the whole idea. Now if you take the commutator bracket, then this with this will give you 0 because m omega by 2 h cut and then x commutator bracket relation is actually 0, plus this with this will give you minus sign of I into 1 by 2 h cut because m omega cancels out, and then xp plus uh, this with this you have to see that this is plus I m omega cancelling out by 2 h cut, then p comma x, and then finally this with this will minus sign, minus I squared is again plus 1, so this is plus 1 1 by 2 m h cut omega p and p. So x and x commutator relation is obviously 0, p and p commutator relation is also 0, so we are left with minus I by 2 h cut into x comma p is plus I h cut, plus I by 2 h cut, p comma x is minus I h cut, which is basically h cut and h cut cancelling out, and I square is minus 1, so minus I square is plus 1, so plus 1 by 2 plus 1 by 2, which is plus 1. So this commutator relation is equal to a dagger equal to plus equal to 1. So our answer is out of the 4 options, the answer is the last option, that is D, that is this is equal to 1. Okay, so with this we have finished 10 questions in the assignment. Let us meet in the next class.